everyone. Today we're going to continue our discussion on radioactivity. So what causes radioactivity? Now, previously we've talked about the nucleus and how it contains protons and neutrons. And I know some of you have asked me before, why do protons stay together in the nucleus? They're all positively charged, so shouldn't they repel each other? And yes, those protons do want to repel each other, but they're held together by something called a strong force. So the particles in the nucleus, again, are held together by a very strong attractive force. And this force is called the strong force. So this force overcomes any of those repulsive forces between the positively charged protons. And this force acts over very short distances. Now, neutrons play a really important role in keeping the nucleus together, or stabilizing the nucleus, because they add to the strong force. Additionally, neutrons don't have a charge. They're neutral, so they don't repel each other like protons do. So what's really important for the stability of a nucleus is the neutron to proton ratio. And we're going to call this the N/Z ratio, where N stands for neutron and Z stands for proton. So again, the ratio of neutrons to protons is an important measure of the stability of the nucleus. So, for instance, what if we have too many neutrons? That would mean that the ratio N/Z is too high. So in that case, an atom is going to be unstable, and they're going to want to turn some neutrons into protons to kind of help stabilize the atom's nucleus. So if the N/Z ratio is too high, neutrons are converted to protons. And remember from last time that this occurs via beta decay. Now remember, beta particles can be drawn with the isotopic notation shown here, or instead of E, we could put a beta symbol there. So either one is fine. But remember, beta particles don't have mass, but they do have a charge of -1. Now, another scenario is that the neutron to proton ratio is too low. So if that's the case, the nuclei or nuclide will still be unstable. But in this case, to kind of reestablish an appropriate neutron to proton ratio, protons will be converted into neutrons. And this is going to occur either via positron emission or electron capture. So you might remember from last time that positron emission and electron capture are the same process essentially, but in one process we are emitting a positively charged electron, and in the other process we're capturing or absorbing an electron, which is negatively charged. Now, this process of turning protons into neutrons could also happen through alpha decay, but it's not as efficient, so it doesn't happen quite as often. Now, in your textbook, there's a super handy chart shown here, and this really shows which isotopes are, or nuclei, are stable and which are unstable. And again, it has to do with that neutron to proton ratio. So on the y-axis, we have the number of neutrons, and on the x-axis, we have the atomic number, or the number of protons. So on this graph, you'll notice a red line, and that line is where the neutron to proton ratio is equal to 1. So you'll notice that for atoms with a small amount of protons, the ratio is pretty close to 1, but then it starts to deviate as we see more and more protons. So just as an example, carbon 12 has a neutron to proton ratio equal to 1. It has 6 protons and 6 neutrons, and that is a stable nucleus. And then up above we have ruthenium, which has 44 protons, and let's see, 66 neutrons, I believe? No, 56. So that ratio is 1.27. And then mercury up above has a neutron to proton ratio of about 1.5. So even if the ratio isn't 1, you can still have stable nuclei. And in fact, there are some trends here that pop up. So we'll go over those. Now you'll also notice that there are some green dots among all of these different yellow dots. Those green dots are stable nuclei, and we call that the valley of stability. So those green dots, are kind of in a valley between two yellow mountains. Okay, so let's go over some of the trends that we see in this chart. So we'll start with the first 20 elements on the periodic table. So if your atomic number is between 1 to 20, stable nuclei have a neutron to proton ratio of about 1. So that's kind of this region here. And then for the next 20 elements, so the atomic numbers 20 to 40, a stable neutron to proton ratio is around 1.25. So that would be in this region, kind of here. And then for the next 40 elements, so for elements 40 through 80, a stable neutron to proton ratio is about 1.5. So that would be sort of in this region. All right. So there are these trends that kind of pop up, and we can see that the neutron to proton ratio isn't always 1. So it can go above 1. But then there are some other rules we can use to kind of, or trends that we can follow to see what's stable and what's unstable. Now, one last thing, notice that if the atomic number is greater than 83, then that nucleus is not stable at all. So that would be basically everything up here. Okay, and we'll come back to this graph later on. Now, last time we saw this chart, table 20.1 in your textbook, and this summarizes all of the different processes that can occur in radioactive decay. One thing that we didn't know about yet, though, was that neutron to proton ratio. So now that we know about it, we can see that if something undergoes alpha decay, the neutron to proton ratio increases. So essentially, protons are converted into neutrons, but that's not very efficient. Next is beta decay, and we can see that a neutron becomes a proton. So that means that the neutron to proton ratio will decrease. For gamma emission, nothing happens because the mass of gamma ray is 0 and it doesn't have charge. And then lastly, we have positron emission and electron capture. And in both of these processes, a proton becomes a neutron. So that means that the neutron to proton ratio will increase. All right, and we'll come back to this table as well. So let's go over an example problem. Let's predict whether each nuclide is more likely to decay via beta decay or positron emission. So let's start with A. We have magnesium 28. And let's look up what the atomic number of magnesium is because that will tell us how many protons we have. Okay, so magnesium is in period 3 and it has an atomic number of 12. So that means it has 12 protons. So we could rewrite the isotopic notation to show the atomic number. Now, if we want to determine whether this isotope is likely to decay via beta decay or positron emission, we need to look at the neutron to proton ratio, and we need to determine if it's too high or too low. All right, so let's calculate how many neutrons this isotope has. Now remember, the number of neutrons is equal to the mass number minus the atomic number. So for this particular isotope, that's 28 minus 12. So that means we have 16 neutrons in this isotope. All right, so now let's determine the neutron to proton ratio. So the number of neutrons is 16 and the number of protons is 12. So our ratio is 1.33. So that's a little high. So let's go back to that chart we saw, and I'm just going to erase some of these markings that I made. So let's determine where this isotope lies on the chart. So we said magnesium has 12 protons, so that's about here. And this particular isotope of magnesium has 16 neutrons. So maybe that's around here. Okay, so magnesium 28 is just above that valley of stability. Okay, so that tells me that magnesium has too many neutrons. We also said that for atomic numbers 1 through 20, the ratio should be about 1, and again, in this case, it's a little too high. It's 1.33. Now, the other way that we could figure this out is by looking at the mass number of this isotope and comparing it to the average atomic mass. So the average atomic mass. So if we had a bunch of magnesium isotopes, what is the average mass? Now that's just what's listed on the periodic table. So let's go back and look at the mass of magnesium. So that is 24.305. Okay, so if we compare those two masses, we can see that the mass number for this isotope, it's just way too high. So that means we have too many neutrons. Okay, so if we have too many neutrons, that means we want to convert neutrons into protons. So let's go to our other chart. What process converts neutrons into protons? So beta decay. All right, so that tells us that magnesium 28 decays via beta decay. So let's actually see what that looks like. So let's write an equation here. All right, so we have magnesium 28, and we don't know what its daughter nuclide is, but we do know that it emits a beta particle now. Okay, so the mass number for our daughter nuclide will be the same because beta particles don't have mass. However, the atomic number is going to change. And remember, we want the atomic numbers to add up to the same thing on both sides. So, what is the new atomic number? It would be 13 because 13 minus 1 equals 12. So, the element with atomic number 13 is aluminum. All right. So again, we're showing that an unstable nucleus with too many neutrons is going to convert some of those neutrons into, or convert one of those neutrons into proton. And that's going to create a more stable nucleus. All right, so let's go over the other two examples. Okay, so for magnesium 22, we already said that the atomic number of magnesium is 12, so we can rewrite the isotopic representation here. And let's determine how many neutrons this isotope has. So we're going to subtract 12 from 22. And that tells us we have 10 neutrons. Okay, so now we can look at the neutron to proton ratio. So we have 10 neutrons and 12 protons. So 10 divided by 12 gives us 0.83. So that's pretty low. So that would tell me we have too few neutrons. Okay, so, and remember, we want the ratio to be about 1 for atomic numbers between 1 and 20. So again, we have too few neutrons. Also, we could compare the mass number to the average atomic mass again. So 22 is our mass number for this isotope. And let's compare that to the average atomic mass of a bunch of magnesium atoms. So 22 is still pretty low compared to 24.305. So again, that tells me I don't have enough neutrons, or this isotope doesn't have enough neutrons. So if we have too few neutrons, this nucleus is going to want to change a neutron into a proton. So it's going to, change a proton into a neutron. Got my words mixed up. So if we're changing a proton into a neutron, let's go back to our chart. Which process would turn a proton into a neutron? Either positron emission or electron capture. So those are the two that can turn a proton into a neutron. Now, in this particular problem, we're asked to determine whether something goes through beta decay or positron emission. So we're not considering electron capture here. So our answer for this problem is positron emission. So let's actually show what that would look like. So we start with magnesium 22. And then again, we don't know what the daughter nuclide is, but we do know that we're emitting a positron. So that's a positively charged electron. So again, the mass number will stay the same. But what is our new atomic number? 11. So 11 plus 1 equals 12. And which element has an atomic number of 11? Sodium. All right, so we're turning a proton into a neutron. Great. All right, last one. C, we're dealing with a different element here, molybdenum, 102. So let's look up what the atomic number of molybdenum is. All right, so molybdenum is a transition metal. So let's look in the center of the periodic table. And it's right below chromium. So it has an atomic number of 42. Okay, so we can rewrite our isotopic notation here. And remember, we want to determine the number of neutrons and then compare that to the number of protons. So the number of neutrons is the mass number minus the atomic number. So 102 minus 42, and that will give us 60 neutrons. All right, so now let's compare that to the number of protons. So 60 over 42. And we get a ratio of 1.43. Okay, so that might be a little high. Let's go back to our chart and kind of figure out where that atom is, or that isotope. So I'm going to erase this line as well. Okay, so we said molybdenum has 42 protons, so that's kind of around here. And we said that this particular isotope has 60 neutrons, so that's right here. So let's kind of guesstimate. All right, so that's right around there. Okay, so that's not on the valley of stability. That's just above it. And we also saw before that for anything with an atomic number between 40 to 80, the stable neutron to proton ratio approaches 1.5. Okay, we're not near 1.5. Okay, so let's go back. Let's also double check the mass number versus the average atomic mass. So 102 is our mass number. All right, and let's look up molybdenum's mass. So molybdenum's average atomic mass is 95.95. Okay. All right, so the mass number is also quite high compared to the average atomic mass. So again, that tells me there are too many neutrons. All right. So what that also tells me is we want to convert one of those neutrons into a proton. And what process does that? Beta decay. Okay, so let's see what that looks like for this isotope of molybdenum. So molybdenum 102 is our parent nuclide, and then we don't know what the daughter nuclide is, but we do know that it's emitting a positron. So it's a positively charged, or a beta, excuse me. It's time for this quarter to end, isn't it? So beta decay, it's a negative particle. Okay, so again, the mass number stays the same. And what is our new atomic number? It is 43, because 43 minus 1 equals 42. Okay, so looking on the periodic table, we'll find that the element with atomic number 43 is Tc. I'm not even going to try to pronounce the name of that one. Okay, so in the next video, what we'll do is go over some of the worksheet problems that I've assigned. So we'll go over worksheet number 2. We'll also go over worksheet number 3 and number 4. But before we do that, let's just go over really quickly some magic numbers that give us stable nuclides. All right, so besides the N/Z ratio, the actual numbers of protons and neutrons can also affect stability. So this is kind of similar to elements with particular numbers of electrons. So remember, the noble gases are extremely stable, and they have very specific numbers of electrons. So helium has 2 electrons, neon has 10, argon has 18, and it's kind of the same with protons and neutrons. So, additionally, a large number of nuclei that have an even number of protons and an even number of neutrons are stable. So for instance, oxygen has an isotope with a mass number of 16, and it has 8 protons. So that means that it has 8 neutrons and 8 protons. And this is a particularly stable nucleus. So looking at the table down below, we have the number of nuclides that are stable, and that's based again on how many protons and neutrons there are. So if you have an even number of protons and an even number of neutrons, like with oxygen, or the example of oxygen up there, then it's stable, and you'll see that there's a very large amount. Now, let's say we have a nucleus with an even number of protons and an odd number of neutrons. The probability that it's stable decreases by quite a bit. So there are only 53 stable nuclides that have an even number of protons and an odd number of neutrons. And then if you flip that, so if you have an odd number of protons and an even number of neutrons, it's about the same probability that the nucleus will be stable. But then let's look at the last example. So what if we have an odd number of protons and an odd number of neutrons? There are only 5 nuclei that are stable. So one of those would be nitrogen 14. So nitrogen 14 has 7 protons and 7 neutrons. And that's one of only 5 nuclei that have an odd number of protons and neutrons that are stable. Okay, so let's say you're trying to predict if a nucleus is stable. If it has an even number of protons and an even number of neutrons, you can kind of assume it's stable. But if it has an odd number of protons and an odd number of neutrons, most likely it's unstable. And of course, there's exceptions to all of those rules. because it's chemistry. All right, so again, only 5 nuclides have an odd combination. Now, if the total number of protons and neutrons, so the total nucleon number, adds to what's called a magic number, the nucleus is more stable. So again, I talked about how some atoms have very particular numbers of electrons that makes them very stable. It's the same thing here. So if the number of neutrons or the number of protons is equal to 2, 8, 20, 28, 50, 82, or 126, they are particularly stable. So looking at the chart on the right, we can see that we have those magic numbers on the y-axis and on the x-axis. So again, the number of neutrons is on the y-axis and the number of protons is on the x-axis. Now, if we kind of extrapolate those up and across, we can see that there are very specific nuclei that are super, super stable. So wherever those lines cross, those are particularly stable nuclides. Okay. Now, one last thing before we go today. We've been talking about different types of radioactive decay. And we did say that atoms with an atomic number greater than 83 are all unstable. So they are all radioactive. Now, we've only been talking about one-step processes, but a lot of atoms actually go through multiple steps of decay. So for instance, in nature, often one radioactive nuclide will change into another radioactive nuclide, and then that radioactive nuclide can keep going. So if you're producing more radioactive nuclides, then they're also going to go through radioactive decay. So this process is called a decay series. Off to the right, we can see that uranium-238 goes through a whole process or a whole decay series here. So initially, it undergoes alpha decay, which is shown by a purple arrow, to produce thorium-234. Now, thorium-234 is also radioactive, and it's going to go through beta decay, which is shown with a blue arrow, to produce, PA is protactinium-234. And then that also goes through beta decay to produce uranium-234. And then uranium-234 goes through beta decay to form thorium-230. Then that goes through beta decay, and so on and so forth. Eventually, we reach a point here where we could have either alpha decay or beta decay. And either way, we'll end up with the same radioactive element, bismuth-214, and that could go through beta or alpha decay, and until we eventually get to our last nuclide, which is actually stable, lead-206. So this occurs for a lot of radioactive elements. They go through a whole series of decay processes until they hit a stable nuclide. All right, and now imagine that each of those steps is giving off energy or heat. That's a lot of energy that's being given off by this process. It's also a lot of alpha particles and beta particles, which we said were pretty damaging to biological molecules. So nuclear reactions can be very, very dangerous unless they are well controlled. And we'll talk more about that later. All right, so we'll end there today, and then in the next video, again, we'll go over some worksheet problems. So I will see you then.